Okay, so I'm sure all of you want to talk about the exam, and we will. I'm going to do that at the end. I'll pass them out. But I thought we would just start with finishing off 12.6. We didn't get a chance to do this. And then at the end, I'll discuss the test. Also, if you noticed on Canvas, it was only showing 3 tests and a final. Yes. So I've changed that, which changed the weights of things, which did have an impact on your grade, I think in a good way, because less grade has been used up yet, at this point. But anyway, we'll talk about that at the end, all right? So the last topic in 12.6 that I want to discuss is these types of problems called inventory control. And these are actually very, I guess, useful problems. They seem to be something a company would want to consider. So here's this fake scenario of a company making DVDs, and I guess we've already had the conversation like this company's already out of business, right? No one's making DVDs anymore, but we could replace DVDs with whatever, right? So a company's making DVDs. The company, I say we expect that we are going to have a total demand of 20,000 DVDs in the year. Okay, so we anticipate that we'll have 20,000 DVDs go out of our doors, all right, and get sold. It costs us 50 cents to store one DVD for a year. So we have to put these DVDs somewhere, right? Put them in a place where they're safe and they don't get broken. So it costs us 50 cents to put one DVD away, store it for a year. Make sense? Okay. It also costs us $200 each time we have to fire up the equipment to make DVDs, right? So you have to set up all the equipment, start burning the DVDs, right? So $200 each time we set up the equipment to make the DVDs. Excuse me. The question is, how many DVDs should be made in each production run to minimize the storage and setup costs? So let's try and understand what's happening here. We have this thing called a production run. So production run is, we're going to set up the DVD burner and we're going to make DVDs, right? We could do that several different ways. Like one way we could do it, let's just talk about some scenarios. One way we could do it, so here's option, let's say option 1, all right, would be first day of the year, right? First day of our year, we decide to just burn all 20,000 DVDs, okay? So let's say we burn all 20,000 DVDs in one production run. Okay? That's one way we could do it, right? Now, what's the benefit to that and what's the drawback to that?
Save on money on cost, but you lose supply and demand because you may overwhelm demand.
So let's assume something here for the problem, all right? This is a big assumption, but let's assume that what we expect is that our demand is going to be constant over the year. So if we have 20,000 DVDs for the year, that they're going to just go away until the end of the year will be at 0. We don't have a peak season where we have more demand and less demand. We are going to assume that there is a constant demand for our DVDs, all right? Now, the pro to this, the good part of this is that we only have to set up the equipment one time, right? So we only have to pay that $200 setup cost once. But what's the drawback? We've got to store 20,000 DVDs and slowly let them get purchased away throughout the year, right? So we're going to be storing a lot of DVDs, but only one setup cost. Okay? Make sense? So maybe that's the best way to do it. I don't know. Here's another option. Now this option is going to seem completely ridiculous, but what if we do a production run every day and only make one DVD? Or not one DVD. How many DVDs, on average, how many DVDs are we selling per day? 20. If we have 20,000 DVDs and we expect to sell all of them in 1 year, So you divided that by what? Like 365? So what did it come out to be? 54.79, so somewhere around 55, let's just say. We're expecting about 55 DVDs to go out our door each day, on average, okay? So one thing I could do, like we said, do one burn of DVDs, make all 20,000 of them, but then they're going to go away by 55 a day. So we're storing a lot of DVDs, right? This way, option 2, why don't we just set up the machine the first day, right, and burn 55 copies, and we'll sell them all. And then we set it up the second day, burn another 55, and sell them, right? So this one would be burn 55 per day, per day, every day. So what are the pros and cons to this?
It's $11,000 each day.
No. Yeah, we don't have to pay a penny for storage, do we?
What you're gonna have to pay.
But we have to pay the setup of $200 every single time we do it, right? So what I'm trying to illustrate are the two extremes. These are the two extremes, right? One burn them all, but then you have to store them all, right? Burn every day, don't have to store anything, but you got to pay to set it up every day. These are the two extremes. What we're trying to do, is there a difference? Is that what you're saying?
Only because I'm doing the burn it all in one drive and I store it for like for a year. So it's since the story, I did that right now. Do that 20,000 times 15, that's $10,000. And I said, burn it.
Yeah, it would cost, if we stored all 20,000 for 1 year, right, then that would cost us $10,000. Agreed? But remember, they're going to keep going down, aren't they? Like it starts at 20,000, but it goes down by 55 each day. So you're not storing 20,000 for a year. It's kind of complicated because it starts to deteriorate, right? We're going to address this. Hold on. That's going to be somewhat expensive to store, but this is going to be super expensive, right? $200 per day, every day.
I times it by 265, that's 73,000.
Yeah. So we're probably not going with option 2, right? Okay, but these are the extremes. The question here, how many DVDs should be made each production run to minimize the storage and setup costs, is saying, hey, look, try and figure out, is there maybe a balance that you can find where maybe you'll do the production run once a month and burn however many, and that will be the best way. So we're trying to minimize the costs, right? Minimize these costs. So just like we've been doing, if we want to minimize something, we can take the derivative, right? Check where it's going. Minimize, we'd want to see where the derivative is negative than positive, right? So the function is going to go down and then up. But we have to come up with a function. We have to come up with a function that gives us the cost. Agreed? Okay, so here's how we're going to do this. What is our cost going to be? Let's just say it in words. The cost is going to be our setup cost. How about that? Setup cost plus, now the setup cost, if I do it once, it's going to be just 200 times 1, right? If I do it every single day, it's 200 times 365. But either way, that's my setup cost. Agreed? And then this right here is going to be my storage cost. So that's what my cost is, right? If we just lay it out in words. It's my setup cost plus my storage cost. Now, let's discuss setup cost. Well, setup cost we said is 200 times however many production runs we have, right? Okay, so what we're going to do now is we're going to start assigning some variables. Just to make our lives easier, let's let P be equal to the number of production cycles or production runs we do, all right? So option 1, in option 1, P is what?
Production runs, P is 1.
P would be 1. In option 1, P is 1, right? In option 2, P is 365. With me? But it's variable. We have to determine how many runs we're going to have to minimize the cost. With me? Yeah? No?
Yes.
Okay. That's what P is. And then let's let S be equal to the storage costs, right? So that's what would make sense, right?
Yes.
Okay. This right here for storage costs makes sense for S. But let's talk about what the storage cost will be, right?
No, it'd be 50 times 55 minus a day, because we're losing 55 a day. We're selling on that even play.
Yeah, we're selling them at an even rate.
So we gotta have a formula that takes the initial 20,000 and removes 55 every day, and the cost of 50 cents.
Is that for the first one, option one, or?
No, we're.
Look, let's do this. The reason that this gets complicated with storage costs is because, like you said, how many DVDs we have in our storage is changing day by day because we're selling them, aren't we? So what I'm going to do, all right, for S, I would actually like us for S to do this. Just follow me on this first example, all right? I want this to be the number of DVDs made in why can't I spell? In a single production run. And you know what? I actually want to change it. Let's change it to X. I don't like that it's S, because S is going to make you think storage, like that's how many we have in storage. Now, yes.
So we gotta pay, I just want to make sure I'm getting this correct. We gotta pay each day to store those 10,000 DVDs. I thought we had to pay like 50 cents for one, and then that's it. for the rest.
50 cents for the year, yes.
Per one.
Per
You gotta
DVD,
take
per year.
Electricity, storage, everything that comes in the space.
No, that's like, so I thought it's gonna be 50 cents per CD stored per year, not pay 50 cents per day for each CD stored per year.
That's right. That's what I said. Yes, you're right. That is correct.
50 cents per store, CD for the DVD for, okay, that's what I'm getting at.
Okay, but see, here's the thing. I need to figure out how many production runs I'm going to have, right? How many am I going to have? Am I going to have one, or am I going to have 365, or something in between? And when I do a production run, I need to know how many DVDs I'm going to make during that run, right? You're kind of on that with me? Kind of? Okay, so we need to look at this, and this is, I'm showing you this problem because it's somewhat complicated. I'm going to try and make this storage cost make sense to you. All right, so I'm going to draw a quick little graph to help you see what's going to happen next. All right, so what I'm going to do is I'm going to, on this axis, this is going to be the production runs. So watch this. Here's 0 production runs. Let's say that I'm going to do 1 production run, 2 production runs, and I don't know how many I'm going to have right now, right? I don't know. I'm either going to have 1 or I'm going to have none. I mean, it's 1 or 365, agreed? Okay, on each production run, I'm going to make X DVDs. So at my first production run, right, when I do my first production run, this is how many DVDs I will have there, right? Agreed? X. That's how many I'm going to make. And then what I want to happen is I want the number of DVDs in my storage to drop down and go to 0 so that when I get to my second production run, all the DVDs that were in storage are gone. Does that make sense? Sure? Then on my second production run, I make another X of them, right? And then I go and it drops down like that, yes? And then on the next one, same thing. And that pattern continues the whole way down. Agreed? So what we need to figure out is what the cost is for storing these DVDs. Yes? Okay. So to do that, what we can do is we can take an average. It's kind of like, think about it this way. If I asked you to give me the area of the area, y'all remember how to find the area of a triangle?
Lane times
1/2 base times height. Y'all heard that formula before? 1/2 base times height. So what would the area of this triangle be? So how tall is it? X, okay? And then how wide is it? 1, right? So the area of that is 1/2 of x times 1. Agreed? Which is just x over 2. Yes? Same with this triangle, right? Same with this triangle, and same with this triangle. All these triangles, right, have an area of x over 2. Do you all follow that? Okay? So even though at some point in time I have this many DVDs here, and I have to pay for that storage, if you look at it over here, later on, I'm going to have a lot less, right? Yes? Okay? So what we can do is we can, instead of trying to figure out the storage cost for the whole piece at each day, so to speak, what we can do is realize that if you just take the average of this, what's halfway between here and here? Half of x, right? This right here, if we imagine a dotted line going across, I know this is difficult, okay? I understand this is confusing. I don't care that you really understand too much of the picture other than to understand the final result. The final result is this. I'm trying to figure out how much it's going to cost me to store these DVDs. They keep on going down and back up, so I always have a different amount in storage, right? But on average, how many DVDs do I have in my storage? On average. Well, in this little interval, the average would be, you might see it this way. If you take this triangle, cut it off, and turn it and lay it in there like this, right? Then basically what you get is that. And that's x over 2, right? So instead of looking at the triangle and how it changes, just say, hey, look, on average, in this first production run, on average, I have x over 2. But then you can say the same thing for the second production run, can't you? It's just however many I have divided by 2. That's my average. And then over 2, the whole way, right? So really, what it looks like is this. The number of DVDs I have in storage is always, on average, x over 2 for the whole year. For the whole year. On average, the number of DVDs in storage is however many I produced in my production run divided by 2. And it's always going to be that for any word problem like this. Okay, you always have to figure out what the average is, which is just x over 2. So, how do we use that? How do we actually use that? Does that kind of make sense? Kind of? Okay. So, when we go back to that formula and we say, what was our cost? And we said this was the setup cost plus the storage cost. The setup cost is $200, right? Times however many times we have to set up, which for us was P, right? It was P? Yes. Okay, P. So my cost is 200 times P plus, now my storage cost, this is 50 cents times the number of DVDs that I have in storage, right? For an entire year. We know they were fluctuating, but we just said that, forget the fluctuating, on average we have how many? X over 2. So this right here, this cost, 50 cents times x over 2, is the cost for storing. It's the 50 cents times the average amount that's in our inventory. Got it? Okay. Now, let's just simplify this a little bit. Is it all right if I change 50 cents over to 1/2? This right here? 50 cents is 1/2. The only reason I want to do that is because I want to look at cost as being 200p plus 1/4 x. Because 1/2 times, you just multiply straight across and you get this. X over 4, same as 1/4 x. I'm trying to find the minimum cost, right? Trying to find the minimum. Now, the problem with that is I have two variables, don't I? My cost has p and x in it, and if I'm going to take derivatives, I need them all to have x. So is there anything that we have not used at all in this information, anything that we haven't used that will help us get rid of P. We did this when we were doing the fence problem. We had to get rid of one of the variables. So is there something in here that I have not used that maybe I can use? I'll give you a hint. It has to do with these two things here. The production runs, the number of times we make CDs, and the number of CDs, the number of production runs that we have, and the number of DVDs we make in each production run are somehow related. What is it?
55?
Close. It's not the 55, but it's related to the 55. No, no.
Is it the RE?
I erased the problem, so I can't point to it.
20,000?
20,000. What has to be 20,000? You're close. It's not the number of DVDs, right? It's not, okay, so 20,000, right, is equal to something, but it's not P and it's not X, but it's related to P and X.
Is it P times X?
This is the total, this, what? What it, is it P times X?
That's what I'm asking you.
Well, I'm asking you.
Yes. I'm gonna go with yes.
I yelled out revenue.
So let's see. Just think about it. If I do 20 production runs, how many DVDs do I have to make each production? If I do 20 production runs,
1,000.
I have to make 1,000 each time. Why? Because you need 20,000 DVDs for the year, right?
Yeah.
So if I did one production run, how many DVDs would I have to make in that production run?
20,000.
20,000,
It's the revenue function.
right?
That's
You know what I'm saying?
Yeah.
So however many production runs you have, times the number of DVDs you make in each production run has to be 20,000 to cover the demand. Make sense? So this is X times P. So it was close. It's not X, it's not P, it's the two of them multiplied together. All right? So we have this relationship between X and P, don't we? So we're over here, let's not lose sight. We're trying to find the minimum cost, but cost has two variables in it. We have to get rid of one of these variables, so I'm going to try and get rid of P. I've got to replace P with something with X's in it. So I come back here and I say, oh, but wait a minute, X times P has to be 20,000, which means P is 20,000 over X, right? If I divide both sides by X, my number of productions should be 20,000 divided by X. So now let's go back over to this and let's replace P with 20,000 over X. That okay? And then I still have plus 1/4 X. Okay, now, my cost is now a function of X. Notice I wrote, instead of C, I'm writing C of X because now everything in here has X in it. So it is a function of X. It is, let's see, what happens if you multiply 20,000 times 200? What do you get, like 4, 0, 0, 0, 0, 0, 0, is that, what, 400,000? 4 million? Yeah, 4 million. Did I miss a zero? 1, 2, 3, 4, 5. Oops. Yeah, I put the commas in the wrong place. 4 million. There you go. 4 million. And then over X, right? Over X. Now I'm going to write that X to the negative 1. Why do you think I'm writing it like that? Because I'm about to take the derivative, right? And I'd like to take the derivative using the power rule. So here it is, everyone. This is my cost function. That's it. I want to find the minimum of that cost function. So we go through everything that we were supposed to know for the last test, which is to find the minimum or maximum of a function. You find its critical number, so we take its derivative, right? So we take the derivative of this, set it equal to 0. So what is the derivative of that?
4 million.
Negative 4 million. X to the negative 2, so the negative 1 came out, then we subtracted 1, and then plus 1/4. Pardon? Yeah, so this right here, derivative of x is 1, then 1/4. So now we set this to 0, right?
Yeah, we can change that to 2.5 or
Yeah, you can change that to 0.25. I'm going to write this now like this. 4 million over x squared. So I'm going back to the notation where I dropped that down. And then plus 1/4 equals 0. And there was a problem that I sent you home with that was similar to this. So we could right now do several things. How do you want to do this?
Move the 4,000 to the other side.
You want to move all this to the other side? I'm okay with that. So this will become 1/4 is still on the left side. On the other side, it becomes positive 4 million over x squared. Okay, everyone understand? Just move that to the other side of the equation, which made it positive.
Yes, now you gotta multiply 400,000.
Yeah, this is where you could do, I think most people call it cross multiplying, where you're going to multiply the x squared over there and the 4 over here. So x squared must be x squared times 1, so x squared must be 16 million, right? Because you're multiplying 4 on this side and x squared. Is that all right or no?
Yeah.
Pardon?
In division.
On the homework it may have been.
Oh,
Yeah, I don't recall. What you're really doing here, like technically what you're doing is you're multiplying this side by x squared and this side by x squared. And then the x squareds are canceling here. And then you're multiplying both sides by 4. 4 here and 4 here. And the 4's cancel here. And so at the end of the day, what you're really doing is multiplying this by 4 and that by x squared, which is the same as cross multiplying. All right, now what? Take the square root. So what's the square root of 16 million? 4,000. Now plus or minus, right?
Yeah.
Plus or minus the square root of 16 million, which equals plus or minus 4,000. Now, what about that minus? Does the minus make sense?
Because it should be greater than 0.
Yeah, we didn't talk about the domain, but remember, X is the number of DVDs we make per production cycle, right? That's what X was? We can't make a negative number of DVDs. So we have, right now, we have a critical number of X equals 4,000. Now, on your exams that I just graded, I saw a lot of students that would do a problem where I ask you to find the local extrema, and you go through all this work, set the derivative equal to 0, and then you got this answer, and that was it. You just boxed it and said that's your answer. There's a problem with that. You don't know if this is a maximum or a minimum. You have no idea right now, do we? It could be a maximum, it could be a minimum. The only way to know if it is to do the number line and test. And so on the test, on the exam, if you did not do number line and test, you lost points. Even though the answer is correct, you didn't show that it's a minimum or a maximum. So I would need to put 4,000 here, and I'd need to pick test points. And so I could pick, let's say, 1, right? And I could pick like 5,000. And where do those get plugged in?
The derivative.
The derivative, right? So here's my derivative, right? This is my derivative right here. I've got to plug in 4,000 into this. Now, I am instead going to look at this right here. Might be easier to plug 4,000 in that. Ignore the equal 0 because that's when I was trying to set it equal to 0. But that's my derivative, right? So if we square 4,000, or no, not 4,000. We're plugging 5,000 in here, sorry. Right, the test point?
25 million.
You get 25 million, is that right? Yes? So what happens there? If you do this number divided by that, you get some decimal. Negative 0.16, and then add 1/4 to it, or add 0.125, and tell me if you get positive or negative. 0.25. Did I say 1.2? You get positive? I'm concerned if we get a positive, because this is going to, if it's positive, what does it mean our function is doing?
You're about to max out.
We're about to go up and then maybe go down. And sorry. My fault. We plugged in 5,000.
Yes.
Right? Okay, sorry, we're on this side. We're going up here. That's okay. That's what cost is going up. Sorry, I was on the wrong side. I was thinking we were going up here, but we didn't plug it. 5,000's over here, right? One's over here. Okay, so we're good there. We're going up. Okay, and then over here we need it to go down, right? That's what we need. So plug in 1, and I think 1 is pretty easy because plug 1 in right here. It's just negative 4 million, right? Plus 1/4. That's a negative number. So that means our cost function over here is going down. And what does that mean? We have a minimum value at 4,000.
Yeah, you got to plug 4,000 into the original, right?
Yep. So the question, the way I phrased it to you is, how many DVDs should the company make during each production cycle to minimize the costs? How many should we make? So do we have the answer to that question? Yes, we do, right? Because this is X, right? X equals 4,000 gives us a minimum. And what was X? X was the number of DVDs we're going to make per production cycle. Got it? So we have the answer. 4,000 DVDs per production cycle. Okay? Now, we would be done with the question, but I'm just curious if we can answer a few more things. How many production cycles would we have?
5.
Where are you getting that from?
4,000.
You go back to the relationship we had. It was 20,000 over X was P, right? Remember that? And so if we know that we're going to make 4,000 DVDs per production cycle, we plug 4,000 in there, and that means that P would be 5. 5. So 5 production cycles. And what's maybe one last question I could ask? How much is it going to cost us to do this, right? So how do we do that? How do we figure out the cost it's going to, the cost for us to do it this way? You can, no, you have to go back to your original cost function. Here it is right here, right? And what do you plug into it? 4,000, okay? So let's figure out what that is. C of 4,000 would be 4 million, right? 4 million, and then this is really over X, right? So over 4,000, so we get zeros cancel here, and then plus 1/4 of 4,000.
So you end up with 5,000.
So this is going to be 1,000 there, right? Because the 4's, so this is 1,000 plus 1,000, this is 2,000. No? Yeah, you're looking kind of, you're okay with that?
Yeah.
Okay.
A lot of zeros.
Yeah, that's a lot. I'm seeing, I did this example out of the book, so I'm wondering if they found the cost there. Oh, there it is, yeah, 2,000. All right, so recap. If we have a company that needs to make 20,000 DVDs and it costs us 50 cents to store one DVD for 1 year, and it costs us $200 to set up our equipment and make DVDs, then the best way to do it, to get the cheapest cost to us, is to run 5 production cycles where we make 4,000 DVDs, and it's going to cost us $2,000. If we do it any other way, we're throwing money away. Does that make sense? Okay. So when I put this problem on the board to begin class, I put 4 stars next to it, right? That's because on page 704, if you look at the top of the page, you're going to see, I know not everyone has the book here, but well, let me say this. If you go to 703, actually 702, then you'll see example 8. And example 8 is exactly what I just did, okay? I just did example 8. And when you get to the end of example 8 on page 704, it says matched problem. And it says repeat the example 8 if costs are $250 to set up and it's 40 cents to store the DVD for a year. Okay? That's due next class if you want a 5-point bonus on the test you just took. All right?
November 12th?
Pardon?
November 12th?
Next class? Yeah, I guess it.
Which problem was it? Example 8?
Page 704. Look at the end of example 8. There's a thing that says matched problem 8. You do that. It's the same problem, okay? But they change a couple of the things up in there, all right?
Do you want to find the same 3?
Yes, oh yeah. And then what I would like it for your answer is I want to know the number of DVDs in each cycle. I also want the number of production cycles you're going to have, and I want the cost. So it's only going to want one answer, but I want all 3, okay?
Wait,
All right, it's all on camera. You can go back and watch it on your own time, okay? I almost didn't record that. I was almost not going to record that and then tell everyone, okay, there's the bonus problem, and then everyone would have been upset. Now, part of the reason I did that also is because your test that you just took were the matched problems from the problems I told you to look at in the book. So I said, look at example whatever, study this example. I gave you the matched problem right below it on the test. What? Wow, right, yeah, that's what I thought too. All right. Not all of them. I think there were 7 problems. I think maybe 5 of them were like that. I need to go back and look. Okay, that's it for 12.6, and actually that's it for chapter 12. All right. So, yay! Wow, you're enthusiastic about that, right? So let's now talk about chapter 13. Integration. Integration. All right, so you know that when we started this class, we started with the idea of the limit. Y'all loved it. And then we went to the derivative, right? We introduced the derivative. We first introduced it as a limit. And then I gave you all those shortcut rules. And everyone was all happy about the shortcut rules. If we look at a function, what we've learned so far is we can do this thing called differentiation, which just basically means we're taking the derivative, right? So if somebody gives you a function, you can take its derivative and get some new function, right? As an example, if we take x cubed plus 2x, and we take its derivative, it would be 3x squared plus 2, right? That's the process of differentiation. Now we are going to study another process, which is called integration. And integration is actually the backwards process. It's the process that takes you from a function backwards to this. Does that make sense? Okay, that's called integration. All right? So it's kind of like we learned how to walk forward, and now we're going to learn how to walk backwards. And in general, walking backwards is more difficult than walking forward. Wouldn't you say? Okay, but good thing is I'm going to give you some formulas, and it's going to make life a lot easier. And I think we can actually help each other try and find the formulas. I think we can create them on our own. But before we do that, let me just write down some definitions for you. So capital F of x is called an antiderivative, not a derivative, an antiderivative of little f of x if the derivative of capital F of x is equal to little f of x. Now I understand that that's probably going to look pretty messy, but just write it down, then we'll make sense out of it. So we have this new thing called antiderivative. So if I give you a function, I tell you, say, hey, look, everyone, here's a function, right? I tell you to take its derivative. I think we're all pretty comfortable, right, with the idea of what you have to do. Now I'm going to give you a function. I'm going to tell you to find its antiderivative. So we're going to reverse it, all right? So let's see kind of how this definition works. Does everybody agree with me right now that that this is the antiderivative of this? Yes? Because in order for this to be called an antiderivative, when I take the derivative of this, right, I better get this. So if I take the derivative of this, I better get that. Do you? Yes, right? Take derivative of this, you get that. Yeah? Now, question. Is that the only capital F that I could have come up with? Can anybody think of another capital F that would have also given me this if I took its derivative? Three.
2x to the third square?
2x to the third square? No.
I don't know, I can't think of it.
Wouldn't it be like 3 over x and then?
I think you're trying to make it harder than it has to be.
Oh, I heard about that actually, antiderivative. It's like reverse.
Oh, just negative x. Negative x.
No.
Or x over negative.
Go backwards in time. Go backwards in time.
Okay. I think once I show it to you, you're going to be like, oh, huh? Plus anything. Plus any number. What's the derivative of that? 3x squared. Right? So the fact that I'm adding this means that when I take derivative, I have to take derivative of this and this separately, right? So when I take derivative of this, I get that. When I take derivative of that, I get 0. But I could have done that for any number, right? That would have also given me this.
Would that be a true or false question? Like, I'm confused on how you would ask that. Would you ask us to write the antiderivative and expect us just to choose a number?
No, I'm not going to ask you that. What I'm trying to illustrate right now is that when we talk about the antiderivative of a function, there's actually an infinite number of functions that would qualify as being an antiderivative. So if I said, hey, look at this function, everyone. Give me an antiderivative, and meaning there might be more than one. Give me an antiderivative of that. Somebody might give me this, and I would say, yes, that's an antiderivative. Then someone else might give me this, and I will say, yes, that's an antiderivative. Someone might give me this, right? So maybe there's a general way that I could write what all the antiderivatives look like. Because all of these look like something. They all have something in common. They all look like they have to have x cubed, right? Do you agree with that? But then I can basically put any number out here, can't I? So what we do is we say plus capital C. Capital C, now I made that capital a little bit too big, but I'm trying to stress that capital C represents any number. It can be 2, it can be 5, it can be 0, right? This is a 0 plus 0 out here. It can be 2, it can be -4, it can be any number you want. As long as it doesn't have any x's in it, it's okay, because the derivative of that's going to go to 0. Understand? So this right here has a special name. It's called the general antiderivative. And that's what I'm going to ask you for, is the general antiderivative of the function.
Okay.
Do y'all follow that?
Yes. Yeah.
Okay, now, again, I think it's critical for us to understand that all of these have something in common, don't they? They all have x cubed, right? So what happens, do you remember what happens to the graph of a function? Like if I take this and I graph it, what would this graph look like? Like how would these two be related to one another? Exactly. This graph is exactly that graph, just up 2, right? This graph is that graph, but down 4, right? So what we wind up having here is a whole like family of functions. They all look exactly the same, but they've all just been moved up or down. Okay? So you get this collection of functions. There's an infinite number of them. All right? But the general antiderivative looks like this. So let's try another example where I'm going to give you a function. I'm going to give you a little f, and I'm going to ask you to see if you can find this. All right? So if I say little f of x is 2x, find the general antiderivative. Find the general antiderivative. So you have to think, like, what do you take the derivative of to get that? X squared, right? X squared. So capital F of x will be x squared, but because I could add any number out here, I'm going to put a plus c here. And just keep in mind, c could be like -2, and then it would be, or -4, and it would be like that, right? So this c can be either positive or negative. That's it. Now, how did you get x squared? I mean, like, how did y'all figure out that it was x squared? Because you know the derivative of x squared is 2x, right? Okay. Let's see how long you can stick to your knowledge before the wheels start to come off. Okay, so how about this? How about if I give you f of x equals, I don't know, how about x to the 7th? So same instructions, I just don't feel like writing that again, okay? What is capital F going to be? The wheels are already off, huh? Okay, so wait a minute. When you take the derivative of something, what happens to the power? It goes down 1, right? So if we want to go backwards, that power is probably going to need to go up 1, right? Do you agree? It's kind of like on this one. It was x to what power? 1. And what happened in the antiderivative? It was x squared, right? So I think maybe, I'm going to leave a space here intentionally. I think maybe x cubed is a good place to start, right? Did I say cubed? I did say cubed. X to the 8th is a good place to start, right?
Would it be x to the octuplet or something like that?
Sure. Yeah, if you want. X to the 8th power. What's wrong with that, though? If I take derivative of that, what do I get? I get an 8 out front, don't I? I don't want that 8 out front. I want that 8 to be a 1, don't I? Like I don't want it there? So what could I do out in front of that would be very clever? Put a 1/8 in front. Ah, so now look at that. If I put a 1/8 here, what happens when the 8 comes down? It goes away to 1, right? And then the power comes down and we get that. Right? Plus c and we're done. Do you follow it or no?
Yeah.
Yeah? So the wheels came off already, but we're going to keep going. Next example. All right. Now, hold on. That's not really x squared. That's 1 over x squared, right? So we need to probably rewrite that first as x to what power? -2. Right? That's what that is? And now let's follow the same principle that we just followed on the previous problem. We know that the antiderivative, the power on that is going to have to go up 1, right? So instead of it being x to the negative 2, it's going to be x to the negative 1, because you're adding 1 to negative 2. So this will be negative x to the negative 1. Agreed? Now let's check this. Will this work? If we take the derivative of this, will we get this? Well, what happens? Negative 1 comes out, which would give us a negative 1 out front, right? And then we would get negative 2 when we subtract. But see, there's no negative here, so how can we fix that?
Change the
Negative one.
there you go.
Just put a negative 1 in front.
Or
Yeah, just put a negative in front. There we go. If you put a negative in front of this, then when the negative 1 comes down, it'll become positive 1, which will be that, and then we subtract 1 from the power and it'll become that. I just work here. You can't blame me for this, okay? Let's do one more, and then I think we're going to try and come up with a formula. So I think our first thing we should do is make this a power, right? X to 1/2. All right. Capital F of x is equal to, now I know the power's got to come up 1, right? So you have to add 1 to that power. What's 1/2 plus 1 is 3/2, right? So, 1/2 plus 1 is the same as 1/2 plus 2 over 2, which is 3 over 2. So 3/2 is the new power. You with me or no? Yes. Okay. But if I take the derivative of that, oh wait, I forgot something over here. Plus c. Sorry, plus c. You have to have plus c. This is not going to work the way it is, right? Because if I bring the 3/2 out, I'm going to have a 3/2 out here, right? And I don't have a 3/2. What do I have out here? A 1, right? So how can I make the 3/2 come out here and it turn into a 1? What should I put out there?
4/3.
Not 4/3.
Or 1/3.
1. Think about it. What would you have to multiply when this comes out front, right? What do you have to multiply it by to make the 3's go away and the 2's go away on the bottom? 2/3. Just flip the fraction over. Look, if I put 2/3 out here, then what happens when I multiply to here, when I actually bring this out? It'll become 6 over 6, won't it?
Yes.
And that'll become 1. So I put the reciprocal out here, and then I say plus c. Yeah? Yeah, okay. All right. I think we're ready to try and create a formula. I'm going to do it with an example, and let's see if it helps. What if we try and find the antiderivative of x to a power? And this time I'm not telling you what the power is. Let's just follow the same pattern we've been doing. Capital F of x will have to be x to what power? N plus 1, right? So we know we're going to have to add 1 to that power. But the problem is, if we take the derivative of this, the n plus 1 comes out here, doesn't it? And we don't want n plus 1 out here. We need to kill the n plus 1. So what we can put out in front of it is 1 over n plus 1. Do you agree that if I bring n plus 1 out here now, it's going to cancel with n plus 1? And then you'll have 1 out here, and then you'll have this power, and take the derivative of that, subtract 1, you'll be up there. And then plus c. This is what we call the power rule for, I said integration was the title of this, right? Integration. That's called the power rule for integration. Let me remind you about the power rule for differentiation. We learned this earlier in the semester. the derivative of x to the n was n times x to the n minus 1, right? That was the formula I gave you earlier? Yes? So that's if we're taking the derivative, the power comes out and we reduce the power by 1. If you're going to go the other way and take the antiderivative of something, you have to increase the power by 1, but then you have to divide by the power plus 1. So, yeah. 20 minutes? Okay. I have one more tricky one for you. Can anybody tell me the answer to this within the next 10 seconds for 2 points added onto your test grade? I appreciate the shots in the dark there. I'm going to give you one more opportunity to think about this, but I'm going to give you a small hint. Can you think of something that we've talked about that you take the derivative of and get that?
Fraction. No, pi. No, square root. No, wait.
No.
Negative.
No. 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 Okay. All right. Time's up. Time's up. Does anybody remember what the derivative of natural log of x is? 1 over x. Do you remember we talked about the logs or no?
Yeah.
It was brief. It was brief. It was brief. Okay. The answer to this is the natural log of x, but I want us to see why the formula doesn't work. Okay? So let's try this. First of all, 1 over x to the 1 over x is the same as x to the negative 1, right? And according to our formula, that would mean that this is n. Do you agree? And if we try and plug that into our formula, we would get f of x equals, according to our formula, 1 over n, which is negative 1, plus 1, x to the negative 1 plus 1, plus c. Right? That's what would happen if I just replaced the n in the formula with negative 1. Yeah? What's wrong with that? What's wrong with this? That's 1 over 0, and division by 0 is not allowed. So what I'm saying to you is, you see this formula over here? This formula works. This formula is good so long as n is not negative 1. If n is negative 1, the formula doesn't work, right? But from what I discussed in an earlier section, if you go back and look, I showed everyone, or I told everyone, that the derivative of the natural log of x is 1 over x. I gave that to you. So the antiderivative of 1 over x is the natural log of x. So for the one case that this formula can't handle, we know the answer to it. So the answer to this is capital F of x equals natural log of x plus c. Okay? That's a special case. All right, I think maybe like 3 more minutes, and then we'll talk about the tests, and I'll hand them out. Sorry? Any points? Oh, on that, no. No one said natural log of x. You tried a lot of different things, though. All right. So do you see on each of these problems, I was asking you to find the general antiderivative, right? But I didn't write it down because it was kind of a pain in the butt to write it down each time. So I'm going to introduce you to some new notation that's going to let you know that we're looking for the antiderivative. Kind of like, you know the notation we used when we had a function and I wanted you to take the derivative? I did that, and that said take the derivative, right? That little prime mark. Or we use like d DY